Okay, we're going to start this first lecture off here, or this lecture, I should say, looking at number 53. We're going to start with number 53. In a 0.1 molarity solution of chloroacetic acid, here it is, it's 11% ionized, and that intends or means at equilibrium. Using this information, calculate the concentration of the ion, the acid, and the original substance. And the Ka for this chloroacetic acid. Okay, so let's go ahead and put this together. We're going to make a rice table to begin this. And instead of writing all of these out, which is a little bit tedious, we certainly could, but I'm going to be a little bit lazy and use a generic for the acid. So the acid listed here, and I will write it out in this way, H plus and A minus. You could switch these guys back and forth, it doesn't really matter. Given the original concentration, it is 0.10. And again, I'm not going to write in molarities. It's kind of implied when you're putting these together that they are molarities. Initially, I don't have any of this present. So I'm going through and saying, okay, well, what did I have at equilibrium? Well, 11% ionized. So if I multiply this value times 11%, 0.11, you will end up with, at equilibrium, 0.011 of both the acid and the salt, the ion coming from the separation. And therefore, this is the added amount and this is the amount that is taken away, the exact same amount from the original concentration. Now again, I can go ahead and write this down because it's right here in front of me, and it looks fairly significant. It's 11%, fairly significant. So I'm going to take these guys and put them into the Ka expression, and I'm going to solve for that. And given the products, putting it over the reactants, I could write these out separately, or I could simply say it's the same value squared, and then put it over the original amount. And I will get 1.36 times 10 to negative 3. There we go. So that is the Ka value, products over reactants, given that. So we solve for it. Easy enough. All right, let's bounce back over to the notes. All right, this one, we'll add another little wrinkle to it. We'll see how this goes. Starting off, we'll say, using a known Ka to calculate the percent ionization. Okay, so the specific problem states, calculate the percent of hydrofluoric in a 0.1 molarity, and this is a separate problem, and a 0.010 molarity solution. And if I look in the back of the book under Appendix D, I will see the Ka value for hydrofluoric is 6.8 times 10 to the negative 4. Okay, so let's do the first part, and we're only focusing on the 0.1 as a concentration. So we will make our rice table. And again, this one, I don't have to be too terribly just doing what I did in the previous problem with the HA. It's HF. Putting down the two products, I have an initial concentration of 0.1. I don't have any initial products being made. And under this circumstance, I'm trying to figure out how much I have. So I'm going to use the Ka value to find these two concentrations and get a percent ionization. So I don't know what these guys are. I'm going to add it and subtract it. Whoops, subtract from here. And again, I'm going to make the bold estimation that it's like about the same amount. I'm going to use a Ka value and say 6.8 times 10 to the negative 4 is equal to x squared over the original concentration. If I do that, I find that x is equal to 8.2 times 10 to the negative 3. Now I'm going to look at the percent ionization like I did in the previous problem. This is x that came from the original concentration. So I'm going to take that and divide it by the original. So I'll say 8.2 times 10 to the negative third divided by the original concentration times 100%. And I will get 8.2%. Now, if you happen to remember from the lecture we had 1 or 2 ago, this cannot exceed 5%. If it does, that implies that, we're being a little too free and loose saying this is insignificant. And this is just like a rule of thumb. There's nothing solid in the math that says one way or the other. This is kind of like just saying, okay, if you exceed 5%, you should go back and find out really what it's supposed to be. Be a little more precise. Okay, so we sort of will. If it exceeds 5%, we can't do the estimation. So we're going to go back and use the quadratic formula. Now, I am not about to go and use the quadratic formula. I've gotten too lazy for that. What I would typically probably do is either have a formula in my calculator, and I have in the past, I don't right now, or you can simply go online and just use quadratic formula computer, whatever it's called, and just put in the 3 variables for A, B, and C. That's usually the way it goes as far as how it's set up with the x squared and the x and the coefficient value or the constant value. If I do that, what you will find as far as the percent ionization given this value, you will find the percent ionization to be, or I'll just say first, x is actually equal to 7.9. And of course, this is the valid answer. Remember when you use a quadratic, you get 2 answers that come out. One, if I'm not mistaken, is called extraneous, which just means it doesn't work. It makes a negative value. It just doesn't make sense. This is the one that makes sense. So 7.9, if I do the exact same problem I did over here, you would end up with a real value of 7.9%. So notice they're really close. This one just is a lot more precise, and it's the one I probably should use. Okay, let's look at part B. In other words, I'm going to look at what if I make the solution less concentrated? So it's 10% of what it was up here. I won't do the entire problem, but if I repeat this process, but instead of using 0.1, I use 0.01 and use the quadratic formula this time, so I just kind of reprogram that back in my calculator, what you will find is your x will equal 2.3 times 10 to the negative third. Or, using percent ionization, you'll end up with 23%. Which is really interesting. So as the solution becomes more dilute, it ionizes more. And it almost doesn't make sense. You're thinking, well, hold on, isn't there more available to ionize with this one? So I should have more coming off. But it actually works the other way around. Think of these things like in solution. You've got a bunch of hydrofluorics, which don't separate well. These are weak acids, remember? So weak acids don't separate really well. So the more and more you put in solution, when potentially they do separate, because it is so crowded, if you will, concentrated in solution, they bump into each other more frequently. And the more frequently they bump into each other, they don't separate well, they bounce and stick back together. But if the solution is really dilute, when they separate, and they're separated from each other, they're more likely to stay apart. But again, as you put them closer and closer together, more concentrated, they will ionize less frequently. So the more dilute the solution, the more ionized it potentially can be. Okay, that's a good place to take a break for the end of this lecture.